tener a Branko con nosotros. Va a dar su charla en inglés, o sea que pues hay que estar atentos cuando consiga. Muchas gracias. Branko, the floor is yours.
Buenos días. Gracias por la invitación. Well, I don't speak Spanish anyway, so you have to do it in English. There's my time. Okay, hi everybody. So I'm Branko. Again, thank you so much for the opportunity to speak to you. We can keep it informal, so if questions come up as I'm talking, just stop me. You know, we can take our time as we go along with this. I figured what I could do today is sort of give you an overview of what we're working on, and maybe have a conversation with you about how that intersects with some of the things that you're already working on. So briefly about our lab. So we're at the University of Michigan, and I'll show you where that is exactly. This is what our lab does. So if it has to do with sensors and data and water, we're kind of interested in it. So we do everything from robotics. There's a little robot that we're building that samples water quality. We do a lot of real-time flooding prediction, a lot of stuff on lakes and rivers, and basically it has a lot of sensors. So if we basically deploy sensors, that's what we're interested in. Today what I want to focus on is this idea of the water cycle. And it must be silly for me to put up this picture because everybody's seen it in like elementary school, right? But I just I love using this to show that a lot of our understanding about water is kind of located up here. This is where I work, right? These like pristine systems, these very clean systems. And this is where I did my PhD. So this is the Sierra Nevada of California. So I studied snow and hydrology, and there's lots to learn there still. But basically a lot of the focus for water seems to have been on these natural systems from a scientific perspective, geohydrology. And the thing that I really got interested in when I started my new job at the university was I wanted to do urban, right? I figured like we seem to know the least amount about where we actually live, right? So here's your typical urban environment, and I think as most of you know because you live here, a lot of cities are underpinned by really complex infrastructure, right? So even a small community of let's say 100,000 people can have hundreds and hundreds of kilometers of pipes, whether that's drinking water or sewers or stormwater. But it's this really complex system, and in a lot of cases it's been built a really long time ago. And a really long time ago means a really long time ago. So here's just pictures of various sewer pipes and stormwater pipes. Anybody want to guess where this is? Yeah, it's Rome, right? It's like the water people always know. It's Rome, but interestingly enough, we haven't changed the designs too much. It's very similar, right? Like pipe underneath the ground. It's been built a long time ago, and it's so old in a lot of cases that it's actually exploding. So I love this picture. I think it's from Taiwan. It's a sewer pipe that basically got clogged. It's an old pipe. Gas built up and it exploded. And this is oftentimes how people who live around this environment realize that there's actual pipes underneath the ground. It's when they're not working, right? Otherwise, when the system is working, nobody really cares, right? So that's one way, is the sewer systems. But one of the things we also like to focus on is sort of like the urban water cycle as it pertains to stormwater. So whenever it rains, most of you know that a lot of stuff just washes into these gutters, and you might walk by them and not think much of it, right? But they're actually there to serve a purpose. They get water away from our cities. And so oftentimes they'll start up here and they'll go into a pipe, maybe a bigger pipe or canal. And as we know from a lot of engineering practice right now, this is wreaking havoc in our ecosystems. It's really tearing up our streams, destroying our rivers and lakes. And it brings up to this idea of, I think a lot of you probably heard the urban stream syndrome, right? The idea that our urban streams and rivers are compromised. And when we look at traditional hydrology, like this is hydrologist view stuff, and this is basically all I'm going to plot today is hydrographs, right? So the flow of water over time when it rains. Natural systems have this tendency to be more slow, right? They're sort of tapered, they have a slow hydrograph, and we think that's nice, right? Urban systems with all the stuff that's on them have this really flashy hydrograph, this really rapid pulse. So when it rains, the water moves very quickly and goes downstream. Somehow that's considered a bad thing now, right? I mean, I think everybody would agree it's probably bad, maybe. But the thing I always like to tell people is that's what we wanted. We designed it to do exactly that. We don't like to have water in cities. We want to get it away as fast as possible. And in some cases, we do a really good job at it. So this is the city of Los Angeles, California. So actually not much, it's like 10 million people maybe, depending on how you count it. Their stormwater system was designed so well that within 1 hour and a half, the whole entire water basically flows into the Pacific Ocean, right? So you could argue that's a good engineering design. If you look at that one storm in the summer, that brings about 10 to 20% of their annual water supply. So then you look at it and go, oh, we could have maybe done something with that water. But if you design a system to just flush it out, obviously you can't keep it. So you need to somehow store it and treat it. And that's a problem, right? So I'm sort of giving you the U.S. perspective of what we're struggling with. So parts of the U.S. are struggling with droughts, right? And parts of them are struggling with just chronic flooding. So I just love this picture, this person just looking into this hole. This is obviously not safe, right? You should never have to do this. But it's just somebody's neighborhood, right? This neighborhood is being flooded. And I just took some pictures from Detroit where I live. This was a big flood that we had a few years ago. And it turns out, like, flooding is the leading cause of natural disaster deaths, right? And it's not like crazy flooding, it's not big flooding, it's like small flooding. Water gets underneath the bridge, and people sometimes misjudge how much water there is. They try to drive through it and they get caught, and that's how a lot of times people get hurt, right? So it's a really big problem, and we're obviously trying to fight it. So that's from a flooding perspective. We also have big ecological problems. So in a lot of cities that were designed, just like Mexico City, a long time ago, the sewers and the stormwater are combined. So when it actually rains, you get these sewer overflows, and this is Lake Michigan where we live, and this is like the beautiful lake, and what you see is sewage just flowing into the lakes. And naturally, whenever you have these kind of impulses of these contaminants going into these ecosystems, it leads to problems like this. So for us, the really big problem are algal blooms. So when we look at our lakes and rivers, many animals and fishes are dying because of this problem, right? A lot of nutrients in our water. And so a lot of cities are aware of this clearly. And basically the idea is that if you have a big problem like this, you want to have a big solution. And these kind of pictures are the reason why I got into engineering, right? I saw this and I was like, this is amazing. So this is a big tunnel in Chicago. I think it cost something like $3 billion. It's huge. You basically put it downtown in the city center where you're flooding it, and you catch all that water. Do you know where this one is? It's yours, right? So big tunnel. It's operational already, right? The really big one? Not yet, but it's a really impressive engineering design, right? And it shows like what we have to do to deal with these big problems. One of the issues, and even though this is kind of exciting, is that a lot of cities don't have the kind of money to build these things. It's really, really expensive to build this. So what I wanted to show you is how a lot of communities in the US deal with this. So I'm going to focus on a community that's fairly small. So this is the state of Michigan, we're in the north, and this is the University of Michigan, so this is our logo right here. I wanted to show you what our town looks like, because even though we're not a massive town, we're about 100,000 people, and we actually get good taxes, and it's a lot of it's an affluent town, we also have problems with flooding. So this is downtown, showing you that even a city like ours, with a few people, has these problems, same exact problems that everybody else is having. They don't have that kind of money to build a giant tunnel. So what do? Well, they do what a lot of people are doing now in stormwater management and flooding management, and they build distributed infrastructure. So the idea is that you go into a neighborhood and you maybe build these things. They look nice, but they actually serve a purpose. They're there for flood control, right? So you might have basins or green infrastructure, most recently, smaller pipes that interconnect the system. And the idea is that if you take these and you put them in a watershed, somehow you're going to sort of improve the watershed. So the watershed I'm going to show you is in our town. So this is the University of Michigan. This is about 10 square miles, so I don't know how much that is in 10 square kilometers, 30 to 50. And what the city does is basically says, okay, I have a problem down here, so all the water's flowing this way. What I'm going to do is I'm going to start installing these things. So I have a problem, so I'm not going to build a big solution, I'm going to build many smaller solutions. So I'll put one in this neighborhood, I'll go ahead and put one in this neighborhood, so I'm just keep adding them. And what I'm going to do is I'm going to keep adding them throughout the city. And somehow if I do a good thing here, a good thing there, a good thing here, it's all going to add up to be a good thing. That's the hope, because we have limited money to do it, right? What I wanted to show you is that really happening? So when we first started working on this, we said, is the benefit that we think we're getting at the neighborhood level actually scaling to the system? And so what I'll do is I'll focus on these two neighborhoods. I'll show you, this is conceptual again. This is neighborhood number 1, maybe they installed this thing. Neighborhood number 2, they installed some sort of bioswale or something. And I'll show you that, so let's say these neighborhoods are draining downstream. So this is the river, all the stuff is going down here, and maybe we had some sort of flooding there. So this is time right here, and this is, let's say, the water level. So this might be neighborhood number 1. So you get this storm coming through, neighborhood number 2, another storm, and they're not adding up, so what you see downstream at this point is maybe a hydrograph like this, right? So now let's say there's flooding in this neighborhood and flooding in this neighborhood, so the city says, let's fix some problems. So they go into a neighborhood and they fix a problem, and you could look at it and say, wow, look, it looks way better, right? It's good. Second neighborhood, that's something good. If you're not careful about timing these now, they might actually add up and give you worse flows than you had before, okay? And this is something that we sort of figured out a few years ago. We read this paper where they took the city with all of these practices implemented, they modeled it in SWIM, and then they went ahead and deleted all of them and just ran a pipe model. So the kind of system you would never design as an engineer, because it sounds crazy, right? The one with just pipes had better flows at the system scale than the one with all these implementations. And that's because we're not designing these systems as actual systems. We're just hoping that if I fix this, somehow it's all going to fix everything. And so, we kind of show this all the time to tell people you have to be careful about this. It's a little bit like economics. If somebody's better off, somebody's going to be worse off. And you have to be able to kind of figure that out. So, so what do we do, right? It's tricky to design systems like this. So our lab goes at it from the data perspective. The first thing we say is, well, let's measure and see what's actually happening. And I use this picture right here. I'm teaching this semester. This is like my 5th time teaching a class on sensing, right? We had some people at the workshop last summer. What I basically teach students is how to build sensor systems for real-time data collection. And this shows you just, in the last 10 years even, we've gone from the analog measurements to things that are very, very small. They can measure, for example, temperature and humidity very cost-effectively in their very, very small footprint. And this ability to measure has been accompanied by a lot of tools to help us get this data out in real time. So not only can you measure, but you can process in real time. You can send that data out wirelessly, cellular networks, whatever you want to do. And so by combining those things, basically you're creating a new kind of paradigm for measurement, right? And so about 2-3 years ago, we sort of put this together into a vision for what we thought, and this is the one you saw on the flyer, which is really nice looking, thank you. When we talk about smart cities, and this is a term that gets thrown around a lot, so smart cities are big things, but what does it mean for water? And so the idea that we sort of thought for a while was, okay, what if you have a city and you start measuring the kind of things that you guys are measuring, rainfall, soil moisture, flows in pipes, flows in canals, to really get an idea about how is the system functioning. Let's see what's happening at the system level. And once you have this understanding, can you actually control it? So instead of just letting the water do what it does every time, can we change what it's doing by controlling it? So the idea is that if we have these 2 neighborhoods that I showed you before, like one is flowing into another one, and maybe you had flooding before, right? So the water spikes up and you have some sort of flooding. Could we put some sort of controllers on this? So think about pumps or gates or some other kind of thing to stop the flow of water and to make realizations like, okay, it's not raining as much in this neighborhood, maybe it's raining over here, and we had this discussion about rainfall variability. You start optimizing the system in real time. So we're not designing infrastructure now and hoping that it lasts 10 or 100 years. We're saying every minute by minute, every second by second, we're redesigning the systems, right? And so that allows you to basically create these benefits at the system scale. And when we first put this idea out there, it didn't go so well at all. I think we heard a lot of ideas about it's too complicated, how are you going to do it? Your reviewers were pretty brutal with us, but I'm complaining now. So we decided, okay, we have to show that this actually works. So we started building it. Okay, so that's what our group does. A lot of our students in our lab have dual training in civil and environmental engineering, and then they also get another degree in computer science and electrical engineering. Now, you don't need both, but it helps in this case to get started. And this shows you our open source platform that we've been working on. So what it is basically, we call them sensor nodes. It's basically a box with sensors, and they're not too dissimilar for what you're using. It has basically a cell phone modem in there, and to it we can basically connect a bunch of sensors. So we can have rainfall, soil moisture, flow, water quality. I mean, I'm just showing some examples. And you put a bunch of these throughout a city, maybe 1 per square kilometer. We really like deploying a lot of sensors. You can have as many as you want, right? That data goes back out in real time, and then we can connect a lot of different control devices. So we've been experimenting around with valves and gates and a bunch of other things that we can control in real time. So that's the hardware layer that we attach to the infrastructure. What we do is we connect that to the internet. So we've been spending a lot of time building server backend things. So basically cloud infrastructure to be able to take that data, process it, and do things like send out alerts to people when there's a flood, for example, or visualize the data, or more interestingly, start running models that can help us control things in the field. So it's very bi-directional. Data doesn't just flow to us, we also send commands back to the watershed. And so with this system, you can start building a lot of different things. So one of the things you can build is, for example, a flood forecasting system. So this unit right here, so here's our sensor node. It's fairly small. It has an ultrasonic sensor that's measuring the distance to the water level. And you take that distance, and now you have it basically all across the system. So this is our network in Dallas, Texas. So this is a region that's been hit by flooding a lot. They actually have a problem with people driving under highways. That's how they die. And so we just put these things all over the place. And so all that data basically streams back, and very quickly, within 1 year, we deploy this large system. And it tends to be pretty cost effective. Because we build everything ourselves, it's not that much. It's like $500 for one of these units, which, it could be cheaper, but it's very cheap compared to sort of like commercial solutions. And again, it's all open source. So we can do this, we can start controlling. And this is where it gets really exciting for us. So you can take a site that already exists. So you're not building anything new. You just take a site, it already has a hole in the bottom, and just put on a valve. Okay? Nothing really complicated, but you still need to sort of put it together. So we have this valve, it's connected to our stuff, and now it's connected to the internet, and we can push a button to open or close that valve. And by pushing a button, you can change the site to look like this, to look like this, right? Completely changes the site. It didn't work that way before. Again, you can do it remotely by pushing a button, but more interestingly, you can control it automatically using algorithms, right? And that's what I'm going to talk about. So these are just some examples that we worked around. So our university's right here. So these are the Great Lakes. They have something like 90% of America's water. It's kind of a lot of water. And what we've been doing is deploying these technologies all across this region. The one I'm going to talk to you about is here. It's the city where we live in. This is sort of our biggest network. And what that network looks like is this. So this is that watershed I was showing you earlier in the city where I said the city's building a lot of stuff. This is actually the one that we studied. And we went in and we said, how many sensors do we need? And we didn't know, so we put a lot. So that was the idea. So we have something like 15 sensors per square mile. This is about 10 square miles. And we're monitoring about like 80 or 90% of the flows in this watershed using these sensing devices. So we're measuring everything from water levels and rainfall, water quality, so your basic parameters like conductivity, turbidity, etc., pH, and then we have these valves. So a bunch of sites are instrumented for control, and a bunch of sites are instrumented for measurements, or for both. This is what it looks like. This is one of our big basins. So this is 5 million gallons. I don't know how much that is in liters, but basically what we did is we went into this basin, put on our valves right here, and by basically opening and closing these, you completely change how the site looks like. And so this is what it looks like when you open up the valve. So this is one of the students opening up the valve. So let me kill the sound actually. So this cost a few $1,000s to do. Now I'm not counting student time, that's not fair, but it's pretty cost effective compared to building a site that's millions of gallons of water stored. So imagine having to buy land, dig up a hole, like build all this stuff. We're just using a site that already exists. And so it looks like the water's coming out slowly, but that's actually on purpose. Because we know in this watershed that when water flows, it stirs up sediment and nutrients and metals and stuff. So by controlling the flow rate, we can actually control what's coming out. So you can control around flooding, you can control around water quality, and the water quality aspect is the thing that's been really exciting for us, because basically we're realizing now that a lot of these systems that have been designed for flood control have a lot of natural elements, like grass and plants that can actually filter your water. It captures sediment, so it's very much like a reactor in a treatment plant, a sedimentation basin. You hold the water, and if you're holding the water for a very long time, all the particles settle out, and then you release it very slowly to go out. And there's a lot of benefit, I think, we still have to explore this, it's all very new, for opportunities like, looking at the city of Los Angeles and saying, capture water locally without giving up your flood control potential. You can still use the system for flood control, but once the storm is done, you can hold that water, maybe treat it and start injecting it back into the ground to sort of replenish the aquifer, because they have that problem. Now, of course, you need to worry about water quality, but these are the beginning phases of this. So a lot of different benefits that can be achieved with control. I could talk about this forever, like what can be done at the site level. But you have to sort of take it with a warning, because like I said earlier, if you can do something really good at the site level, you can really mess up the watershed. So what can we do in the big watershed? And so I kind of wanted to show you how we control this site. So again, 5 million gallons, multiply that by 4 and you get liters. What we can do at the watershed level. So basically we have our site that we're controlling right here, and a few kilometers down is a wetland. So this is the city's like crown and jewel. They put a lot of money into it, and what it's supposed to do is it's supposed to take the flows from this basin right here, and it's supposed to treat them. So the water is supposed to flow through here, and sediments and nutrients are supposed to be removed by this wetland. Problem is, whenever it rains, water comes from here, it comes from here, it comes from all over the place, and it actually overwhelms the wetland and it floods most of the time, right? So the typical problem is we only have so much money, so we can build what we can build, and it does what it does, and oftentimes floods. So what we thought is, we're not controlling that, they won't let us control it, but we can control this. So could we put a sensor down here, and then just control this one whenever this is ready to take water, right? So we put a sensor down there, it's measuring water levels, and what we're doing is we're basically sending water down only when we know the site is ready to take it. So keep in mind, these things are almost like 3 to 4 kilometers apart. So this is the site right here. We captured, as I said, about 5 million gallons of water, so 20 million liters. When the storm was done, we opened the valve. Okay, so we're holding that water upstream, and what you're seeing here is basically the water level in the upstream basin, and when we open up the valve, the water's going to start draining. So the water levels are decreasing in the site, basically. And about an hour or two later, that water goes downstream. We can detect it. So this is basically saying we're controlling something that's really far away by just using one valve, right? So it's kind of exciting. When we first started showing this data, I always complained that people didn't believe us. They're like, well, what are your sensors measuring? Are you right? And so we decided, okay, we have to actually take videos for people to believe that this is happening. So we went down to that wetland, and we took this video. So this was about 2 years ago. You see the water levels, and they're slowly going to start changing, and because it's not raining, we know that the only thing that could be causing that change is us opening that valve. Okay? That's a few kilometers apart, right? So we're controlling a site by not controlling it, if you want to think about it. It's really sort of bringing on the system scale approach. So the benefits start scaling, which is, to me, the most fascinating approach. So you could say, okay, well, yeah, I'm doing something here. What am I doing? I'm holding water. By holding water, I'm capturing sediments, so that's pretty good. I'm actually removing that water downstream. So now that 20 million liters that were going down here didn't go there during the peak of the storm. And then on top of it, they were filtered by the wetland. So by just having one valve, we have this cascade of benefits that are adding up throughout the watershed, showing us that it's actually possible to start controlling things across pretty large scales, across systems that were not designed for this purpose. They're just there to do what they're supposed to do, right? They're engineered systems. So that brings me to this idea of like, well, what's next? What do we do with these systems? And I think this is where the exciting research problems are, at least for our lab. Basically what we're trying to figure out, and I hope a lot of people would get interested in it, is this idea that we know a lot about water systems. We've studied water systems for 100 years. We have 10 or 20 years of really good knowledge of hydraulics in urban environments, equations, soils, all these different things. But how do you take that and embed that into actual algorithms that a computer can understand for real-time control, right? We want to control these systems, and we want to have sensor measurement streaming in. We want to make decisions on a second-by-second basis. Well, traditional water models are not designed for that, right? So what we have to start doing is basically we have to start building simulation engines to actually start showing what could happen at larger scales. And so that's what we did. We basically took a water model. This is the stormwater management model, or SWIM. So how many people are familiar with this? SWIM? Okay, a couple of you guys. I know you probably, do you use it at all for your research? Yeah, so SWIM is great for modeling physics. It's not so good for sensing. It's not so good for controls. So whenever you want to do real-time controls, SWIM is not designed for that. So we built a custom version of SWIM that basically what it does is it takes the model, pauses at every time step, and then allows you to use your favorite programming language, so Python, MATLAB, whatever you want, to start building system-level control algorithms. All right? So we basically just took the SWIM engine, pulled it out, and made it into a controllable system, and that allows us to start implementing like pretty fancy control algorithms that were never part of SWIM. So we're using what we know about water, but now we're moving it to a different area for real-time control. And this allows us to start implementing lots of cool new control algorithms. So the first one we looked at, or one of the first ones we looked at, has to do with self-driving vehicles. So at our school, we have a lot of research. This is where all the fancy research is, like the self-driving cars. I see them, they drive by my house, and it's kind of exciting to think that my kid is never going to have to drive, hopefully. So they have a lot of sensors on them, and they're driving around, they're trying to figure out, and it's a pretty complex problem. The car's driving around, has to figure out where to go, how to turn, and there's a lot of different methods to do this. And one of these methods deals with sort of machine learning. It's like deep learning networks, so specifically reinforcement learning. And to sort of give you an idea about how that works, a good way to start off with is a video game. This is actually how they built these systems. So I don't know, a lot of you students probably have not seen this before, right? This is like a pretty old game, but I still remember it. This is the premise of the game. You have all these bricks, and you have a paddle at the bottom, and you're just moving it back and forward, right? So at any given point, whenever the ball is moving, you have to decide, should I go left or should I go right, right? And so it turns out you can give this problem to a computer. You can say, here's all the information that's on the screen, and you decide when to go left and right. Now, there's a branch of machine learning that basically deals with what's called reinforcement learning. Instead of sort of writing a big sort of complex formulation of this, what you do is you just give this game to the computer. The computer's going to play it a million times until it figures out what the right decision is. And that's how they, playing chess now and all these cool things. But basically what you do is this. You pretend like you have a human in the loop. The human interacts with the world, and it basically does something to the world. Maybe it opens and closes a valve or plays a video game, right? And then it sees what happens, and then it changes what it does, and it does this million, a trillion times over until it figures out the best control strategy. And so this is called reinforcement learning because you're basically trying out a lot of things until you figure out what works, right? You could argue from a water perspective that sounds really dangerous, right? We can talk about that. So anyway, you take your world, you put it in these action states, and then you learn these functions basically that try to figure out using a deep neural network essentially how to move that paddle, or in our case, how to control stormwater network. And this stuff came out a couple of years ago. It was really big. I mean, Google was, I think, at the forefront. What they did is they bought all these academics and they put them in a big lab and they said, just go at it. And they figured out how to play video games way better than a human can play. And so our idea was, can we just replace the video game with a SWIM model and see what happens? And so we did. So here's your SWIM model of the system. So this is like a slightly scaled down version of the watershed. And we said, okay, you're controlling these valves right here. Let's apply this controller And what it basically does is it runs swim, the model. Okay, you would never do this in the real world because you don't want to just try things and flood a neighborhood, right? And then you have this neural network that's basically learning how to control this. And obviously, if you have to try many different things, it takes a lot of time to do it. So if you think about even a simple system, so let's say this system, it might have only like 10 places where you're controlling, and maybe you're not controlling at a fine scale. You're only deciding at every time step, should I open my valve? You know, should it be closed, 10% open, 20% open, 30%? So 10 different states for each valve. For 10 valves, at any given time step, that's 10 billion different combinations. So the problem just explodes immediately. So you need fancy algorithms, but you also need computational power. So this stuff for us has to run on these graphical processing units now that these neural networks require. It's the only way to do it, and it still takes about, I don't know, a week or two to really train a controller. But we basically give this control problem to the system, and what it does over time, it learns how to control. And the way we do it is we give this computer a reward. So we say every time you do a good thing, like you don't cause flooding, you're going to get a reward, and every time you cause flooding, we're going to give you a negative reward. And you can see after a while, and this is many, many iterations, the computer slowly learns the optimal control strategy based on this problem, right? So it's kind of nice because you can just feed the model to the computer and it learns it. And it turns out that even for these small watersheds, it can figure out very quickly how to give us these hydrographs that we want. So we wanted to show that you can go from a hydrograph that's spiky like this, like the ones that we don't like, to something that might be more gradual. So what we told it was basically rev it up, hold it constant, drain the watershed, and then go back down. So basically if you know that it's going to flood right here, or you're going to cause erosion, or you're going to have some sort of water quality impairment, you control around that. Okay? So that's reinforcement learning, it's machine learning. I'd love to have a discussion of should we trust computers to do this, but it's one way to do it. If you don't like self-driving cars, another algorithm we're trying out has to do with jet fighters. They will not, these things cost a lot of money and they're not going to put a neural network on there. So what they've done is they basically said, we trust the things we know, we trust physics. So if we know how an airplane flies and we know how great gravity is and all these vectors are, we're going to start building control models. And effectively what you do is you say, I have a really complicated water system, but do I really need to model it in that way, right? Do I need to use SWIM or some of these complex hydrologic models to basically figure out how I should do control? Could we instead learn a much simpler model, right? And the analogy I always like to give people is, each one of us knows how to take a shower in the morning, right? You go in the bathroom, you want some optimal temperature, but you don't need like a perfect hydrodynamic model of your house to get the perfect temperature. Instead, you go in there and you move it left and right until it's right. That's called feedback, right? That's how control is done. Control says, I don't need a perfect model. Where my model is bad, I'm going to make up for it by opening and closing a valve and pushing the system to where I need it to go. So that's sort of like that branch of engineering, and it basically takes the water system and represents it as a linear system, and that's what we've been doing. Now, of course, from a water perspective, you could argue day and night is a linear system of good representation, but again, for the shower, you only need very simple states too. So what we do is we basically take the water system and we start representing it as a sequence of reservoirs, right? So we basically say, okay, there's a reservoir right here, it might be in series, it might be in parallel, and what we're doing is we're basically measuring the water level in each of these, we're measuring the flow, and we can construct a full stormwater system out of this simple representation where all you're doing is you're basically modeling how fast the level is changing and how fast the flow is going out and how the system is interconnected. The technical term is called an integrator delay model. So you're basically integrating at each storage basin how quickly the water levels are changing, and then you incorporate the delay. How long does it take for water to flow from one part to another part? You can put that in a nice little matrix equation. I have to have some math on here. But basically, you put all these flows and these water levels in this matrix equation, and you can start creating full matrices that represent your full water system. Okay? So you take something really complicated like SWIM, and you actually parameterize it as a fully linear system of flows and heights, and then you also basically input the valves. And the idea is that if your system is a linear system, like right here, that's modeling your dynamics, your linear dynamics, and then you have your feedback in here that basically decides when to open and close the valve. And just like the shower example, if you keep moving it until the temperature's right, you're pushing the watershed, the whole entire watershed now with however many valves you're controlling, back and forth until it sort of moves the system to some desired state that you actually want to achieve. So these are tools from control theory, like mechanical engineering, right? They use this in process control, they use this for autopilots, they use it for all sorts of control systems. So basically you formulate this, I know I'm jumping through the math real quick, but basically just showing you it's there. It's actually an open source toolbox that you can use if you want to. But we can formulate this as an optimal control problem and solve it using something known as a linear quadratic regulator, which basically, if we go back to simple terms, says I can take a watershed, model it as a much simpler system, a linear system, and that linear system, I can basically start putting it into the real world now and start seeing, can this actually control a watershed? And so through simulation, we can now take these big watersheds and show what would happen when you have 2 valves, 3 valves, 10 valves, or for a really big city, thousands of valves you got to control, right? And we can provide safety guarantees and all this other stuff. So, kind of exciting from a modeling perspective, but the thing that, again, only matters is, can you actually do this in the real world? So, I want to go back and sort of just close out by showing you this watershed that we're working in here. Again, 10 square miles, so we have the outlet right here, and we have a site that we're controlling, actually a couple sites in this case. And what we wanted to do was show in the real world that we can go from this hydrograph, right? This is the hydrograph that we observe in the system, to something that looks like this. We want to bring the flows up, keep them steady, and pull them back down. So the reason why that's good is, number one, flooding, because if you know it floods at this level, you're not flooding downstream. Another reason is sedimentation. If the flows become too fast in their watershed, they store up sediment and metals and all this other stuff, so we want to prevent that. So we carried this out. This was before the winter, so we can't do experiments. Unlike here, we can't do experiments in the winter. Everything's frozen for us. It's very, very cold. So here's our data showing that it works. And again, to show the people who don't trust our data necessarily that it works, we were really lucky. Our federal government has a stream gauge right here. It's really rare. They're kind of pricey, but they had it there. So we have a federally validated thing that shows that we can control a big watershed. We bring the levels up, hold them steady, and bring them back down. This is just a few students doing this, okay? It's like we're basically just given permission by the city, which is ridiculous. I still wonder like why they trust us with this, but I'm really grateful. Like we work with the city of Ann Arbor and the local county where we're at, and they're really our collaborators in this project, but showing that this is possible. We can control an entire watershed with just a few valves, okay, using existing infrastructure. So the cost ramifications are quite significant. So we showed that this was possible, and I was talking to students, I said, well, what are we going to do next? Like, this was the goal of the project, now that that's doable, what should we do? And so I came to the lab one morning, and I saw this flow pattern right here. Anybody want to guess what that is? It's our school logo. They wrote our school logo in the water, okay? So somebody at our federal agency is probably looking at the flows and going, what in the world? Like, students are spelling their names or something worse, right? It might seem silly to do this, but when you show this to somebody at the city, they know what's going on. It's basically, they know that if you can spell letters, you can start doing all sorts of meaningful things, right? And so that's kind of where we are with this research. It's really trying to figure out, okay, now that we know it's possible, I know that's not good science to say something is possible, but we can start writing hypotheses about how to actually construct these systems, okay? So, well, I kind of just want to close and say, like, well, how does this scale? So I showed you what works for our little watershed, 10 square miles. You have a really big city. How big is Mexico City? Do you know the area? Pretty huge. Okay, it's very big. I pulled out the map. I kind of tried to scale it. It's pretty big, right? Okay, so this is where we are. This is the biggest city next to us. It's Detroit, Michigan. You might hear about it in the news. It's a fairly large system. So this is their urban drainage system. It's really big, and I can put scale bars on it to show you like how big this is, but it's hard to appreciate. So what I wanted to do is put your city next to it to show you how big it is. So this is the scale. So this is a regional system. We have the city, but the whole entire region's sewer system and stormwater system is run by one entity that we're collaborating with, and it's a fairly large scale. I mean, you guys are obviously infinitely more complex and larger, but just to show you that this stuff is actually starting to be implemented across these large scales. So we're working with the city, and we had these conversations earlier about when you work with the city, how do you go about it? The first thing we always find out is that these cities actually have data in a lot of cases. They have sensors deployed throughout their system that are measuring water level and other things. They're not really using it other than for like things that they're interested in. So they might want to know what's the water level here, so I can send some guy over there to open the valve manually, or maybe I want to charge somebody for their monthly bill. But that data just sits in a silo. And what we've done is we work with the city, and we basically take that data and we put it into real-time models. So that's step number one. Without even deploying any measurements, we could add our own if we wanted to, but we take this data and we start building the kind of models that I just showed you. And why that's great is you can start using control at a much larger scale. So this is a tunnel in the city of Detroit. This is really large. So this is, I think, 18 feet or 20 feet, which means you could fit two of me in there, probably as high as the ceiling. What we have here is not a valve, but it's a pillow that you put in. You inflate it with air, and as you start filling it up, it's holding the water in the pipe. So the pipe actually has a lot of capacity. And this is in extreme cases when you have like rainfall variability, right? It's raining here, not over here. Why not capacity and hold the water? And so it's exciting to know that this stuff is actually going to much bigger places and could be applicable as we look at different cities. And so to close, It's exciting to work on this, but you still have to do a lot of convincing. This is not how this is done usually, right? So when you go to a city, you tell them, hey, let me like put some students on here. We're gonna have robots and self-driving cars. They usually say like, just get out of here. Let me do my job. So we had to figure out how to speak about this stuff in a way that makes sense compared to other solutions. And so the way we like to talk about it is in terms of traditional infrastructure. So when we think about infrastructure, we know that any infrastructure, no matter where you are in the world, is going to fail at some point. So here what I'm plotting is storm intensity, so how strong a storm is. This is storm duration. And so basically, any given point, your system's going to break, whether it's a real-time controlled system or whether it's any kind of system. If the storm is too long, it's going to break. If it's basically too strong, it's going to break, and there's this in between. The way we think about this is that real-time control is going to push your infrastructure to do more than it could do before, right? So we have simulations that basically show that if the city floods every 10 years, by using real-time control, it could flood every 30 years, right? Another way to think about it is if you have to build new infrastructure, some of our simulations right now at least are suggesting that you can make it at half the size by using real-time control. So the cost savings are quite significant. So basically by adding a valve, you can build much smaller infrastructure and start building it in places where maybe you wouldn't have thought about building it before. So that's the kind of terminology, and there's obviously a lot, as I said. For us, this is very, very new. Still not too many people working in here, but I think it's exciting. There's lots to be done in control algorithms. There's lots to be done on just social interaction. So like, we need to work with social scientists actually to figure out how to convince cities that this is safe and it's doable. But I'll just close with that and say, again, thank you very much for the invitation. This was all constructed by students. So everything you saw today was built by students, deployed by students. We had a workshop last summer under this open storm project that we started. So everything's freely available. You could make it if you want to. And we had people who came to the workshop, and we had like a couple of days in Ann Arbor where we learned how to do it. But this is the crew right here. So with that in mind, I'd be happy to take questions.
Any questions? Okay, don't be shy. Any questions? Anyone? You can use it.
So that you use a GPU for the with Swim.
Yeah.
Did you change the Swim model to run on GPU, or it was just the machine learning part that was on the GPU?
So the question is basically like we use the GPUs, and as I said, we need it for neural networks. We're not, like the hydraulic models are not configured to work with GPUs, right? They're like still running a regular processor. That ends up being the limiting factor. But we are working with another project called Open Water Analytics. It's an open source version of Swim that runs on Python to build in parallelization, right? So we're still not there yet. We figured out a way to simplify the Swim model to get it to run fast. The computational power is still on the neural networks. Those things just gobble up computing power. So that runs on the GPU, but Swim still runs on the regular processor. And what we do in that case is we just run 200 processors, and we can run Swim in parallel like that.
But I have actually a follow-up question. You are working on OWA for a GPU version of Swim?
So no, not the GPU version. Actually, I think step one is just parallelization, right? So OWA, there's a couple of different groups working on Swim. Sounds like you probably work on it too, right?
Yeah.
There's like groups in Europe. There's a group in Texas that got a big center funded to do Swim development, and then there's OWA, and then there's a couple other people. We're all working on different things, right? Everybody's thinking about parallelization in a different way. The GPU version of Swim, I actually don't even know how you would go about that right now. The first step is actually just regular parallelization, right? It still doesn't support that very well.
Yeah, it ran on OpenMP.
Yeah,
that's not.
It's there. So we ran a version on OpenMP. So for those of you, this is the parallelization framework that puts the models together. What we've seen is that unless you're running a massive, massive system, the parallelization doesn't even help you. Like the startup at the beginning of adding the parallelizing and the threads and all these other things slows you down so much that the benefit, like we only got a 14% speed up when we did the parallelization. So there's a lot of work to be done there. And we should talk more about it. It sounds like you got some ideas. Yeah, thank you.
Do you have an estimation about cost on controlling an entire city?
Yeah.
This kind of project?
Yeah, so the question is, how much does it cost to control an entire city? I got a similar question a couple of weeks ago. Like, if you took the whole city of Houston, which probably is, you know, in terms of land area, similar to Mexico City, I don't know. It's like when we first started working on this, we're like, oh, we're gonna put a valve here. We didn't know what we were getting ourselves into. And now the question is, how many valves do you need and how many sensors do you need to go on the entire city? We're going like baby steps, right? Like, first figure out how to do 1 square kilometer, 2 square kilometers, we're up to 10 already, right? Moving up to 20. There's going to be a lot of complexities. I think we can figure out the engineering question. We know, for example, that for 10 square kilometers, you only need 2 or 3 valves, and after that, there's no more benefit, right? You can't get anything more out of the system. You can't really scale that to a city, though, because number one, you're going to run into like political stuff immediately. Water does not respect neighborhood boundaries. So what one neighborhood wants to do is not what another neighborhood wants to do, which means your control algorithms like throw them out, right? So there's a lot of challenges that we have to overcome. So from the engineering perspective, we keep working on control algorithms, and we're gonna figure that out. But we also have to figure out how to deal with multiple ownership boundaries, watershed boundaries, all these different things. So I guess my answer to you is I don't know, but you know, let's figure it out. So.
Okay, and second question.
Sure.
And well, you need a big power up of computer systems.
Yeah.
So, do you have an estimation or an idea on how to control in big scale, for example, in concentrate or different sites?
Yeah.
Because it's kind of difficult, no?
Absolutely. So actually, thanks for asking that question because I should clarify it. You need a lot of computational power at the beginning to learn how to control. Once you actually have the algorithm designed, then it's super fast. It can actually run on these little units that we have. So most of our control algorithms run as a simple Python script that can run as fast as a computer can go, actually. So the computational power becomes quite a simple thing. Now, if you want to get into more complicated algorithms where you're reconfiguring the algorithm in real time and doing some really fancy stuff, then you have to start worrying about it, but we're not even there yet, right? So now we know we can run simple algorithms fast, and then we're going to get, we're going to see where that takes us. But it's very doable. Like, I think we can control the whole city now, if somebody lets us.
Thank you.
Yeah.
Anyone else?
Besides the benefits of implementing such a system, isn't there also a risk that by this, by adding all these sensors and valves, you're getting a more complex system? Is there a bigger risk that if one of these components fail, that you get even a bigger flood in some cases?
Yeah, and I think that's something. So basically the question is, when you introduce technology, you open yourself up to failure, you open yourself up to hacking, cybersecurity, all these different things. It's something we have to deal with, because the way I view it is, self-driving cars are coming, for example. Like, it's unavoidable. Like, you're going to be in one like 10 years from now, 5 years from now, whenever they're ready. We have to figure out how to deal with that, because the benefits that these technologies give us are going to come with drawbacks. The thing that we have a tendency to do as engineers, I think, is to say, well, let somebody else worry about security, or I'll worry about it when I figure out how to build control algorithms. Or even worse, I'll worry about the social problems when I figure out the engineering. And I think you make a really good point. We have to start doing that now. So we try to do our best when we're building this. We try to sort of say, okay, we have various fail-safe mechanisms. So if a valve fails, we can go and push a button on it directly on site. We can crank the valve to open it. Like, we can do all these different things manually. But at some point, you also have to start building control algorithms that are robust to failure. So if we, for example, detect that a sensor has failed or a valve has failed, you have to do something else with your system. And those are the kind of control algorithms we haven't even started looking at, right? What if somebody's attacking your system or doing something sophisticated to it? We have to figure that out. The way I view it right now is that, yes, there's risks, but we know stuff about these systems now that we didn't know before. Before, a pipe would clog, and you would know about it for like 10 years. Right? Now, if it fails, we know it's failed, and we can try to address it as we go along. So just like any other engineering system can fail, this can fail also. We just have to figure out how that compares. So, we gotta look at it. Really good point.
So yeah, following his question, and about this, like the risk of failure and cybersecurity and For instance, if you apply this, let's say, new way of operating water infrastructure, and for instance, if you do for some like really important, for instance, water supply, and assuming that the water supply would be in risk, assuming like a cyber attack or something like that, have you, or what are your thoughts about perhaps using a decentralized system? For instance, using this, I'm right now, for instance, I'm thinking about a blockchain protocol in order to centralize like the water management of a urban or a city. What do you think that somehow it could have any future or?
Yeah, so the security of how you build these things is absolutely, again, as you say, really important. Now, how we're going to do that is, I still don't know. You know, we have to figure it out because we're not there yet, but we're getting there, and things seem to be moving fast. So some sort of decentralized approach intuitively would seem like it's good, right? Because then you're distributing the risk and all these other things. I think that's naturally going to happen because different communities are going to own their own water system. They're all going to want to do it however they want. So everything we've built so far assumes some sort of centralized architecture. Now, at the scale of 10 to 20 to maybe 50 square kilometers, beyond that, you might want to operate two. But again, you get benefits with centralized. So this whole trade-off is very unclear at the moment. But something needs to be developed to enable that. Right now, we don't even have standards. I mean, we're not even talking about like blockchains. We don't even know, like one sensor is built by one company and it's operated by like this neighborhood. Another one is operated by different manufacturers. They're not even talking to each other. So we have basic problems of just communication. Then we have, what if you have multiple valves? How are they going to interact? And then we're going to get this issue of scaling and decentralization. So I think from a research perspective, that's the kind of stuff we need to start looking at now so it's ready when the time comes. But we haven't yet, right? So come join us.
I do have one. Sure. As I was seeing your strategy of using a control theory to these systems, I was thinking of uncertainty. What about it? You know,
Sure.
Because you may be controlling something that is ideal.
Yep.
It's a representation of something of a system that may not be working as designed, as we were just talking about. So how you can incorporate this uncertainty in this strategy?
Yeah, absolutely. So basically, the idea is that we're simulating stuff, assuming a perfect water model, which is great engineering. It's like, look what I designed, it's working perfectly. And then you put it in the real world, and the sensors doing up and down and crazy stuff. We're working on that actively right now. I think that's actually one of our bigger research challenges from a control perspective. So there's uncertainty in terms of, are you even representing the system well? Then do you have sensor measurement noise? As you know, there's rainfall variability. So if you use one sensor to capture rainfall, very different than when you use 10, right? You have different knowledge. Weather forecast. So we just finished writing a paper on weather forecast showing that if you know what the weather forecast is, you can prepare the system. So let's take the city, for example, and say we're storing water. You don't want to store water because when it rains, you're going to flood the system. But you want to store water because you want the water. So you could look at the weather forecast and say, oh, I only have to bring it down like halfway, and then I'm going to capture that new stuff that comes in. But as you know, working on rainfall, weather forecasts are like, whatever, 50% accurate or something, right? So if you have the perfect forecast, it works well. So we did a study where we basically just started introducing noise to the forecast, and you can still see it still provides you benefits. Even if the forecast is not exactly right, on average it's right? And so you start playing statistical games. But again, very early on, so you have to start building, as you're pointing out, algorithms that are robust to various kinds of uncertainty. And until we start building these in the real world, and until cities start building them at scale, I think it's going to be even hard to know what those are. So we can simulate them in models, but until we start controlling real systems, we're not going to know how big the impacts of that are. But it's a really important thing to do because we have to guarantee that these things are not going to flood neighborhoods. So,
thank you. Anyone else? Talk now, or we can call it a day?
Yeah, I'll be around too if people want to talk.
Yeah. Thank you very much,
Sure.
Branko.
Thank you.
It's a pleasure to have you. And I'll give you, it's a tradition in the Institute to give you a little present for the talk, for the effort, and a little diploma just for you to make sure that you work with you. Thank you very much.